Hi Wildcats, Mr. Weber here with Unit 9 Focus Question 1 Notes Overview. In this unit, we're going to talk about work and energy. That's Unit 9. In Unit 8, we looked at forces and Newton's laws, and something that we saw is a force is required to accelerate an object. And so, if you push something or apply a force to something, it takes energy. So then energy and forces must be related. And that concept is called work. So we'll talk about when a force is applied and causes a displacement. We'll talk about, so we say lots of things are work, right? Homework. This is a lot of work to sit here and read for an hour or sit here and listen to me drone on about work is work. But it's not. We use that term colloquially. I can't say that word, apparently. We use the word work, but we don't use it correctly. So scientific work is different than what we call regular work. So here is me. This is how I'm spending my quarantine. In this picture, I am doing absolutely no work, while this motorized tricycle is doing all the work. And so really to understand how it is that he's doing no work and the trike is, we need to take a moment and think about what work actually is scientifically. So, the definition of work scientifically, or in the physics realm, is work is the product of a constant force which causes a displacement. Or in other words, work is equal to force times displacement. So whenever a force is applied and it causes an object or is related to an object's displacement, that is what we would consider scientific work. Another way to think of this is with Newton's second law. So we could also say force is equal to mass times acceleration times displacement. This would still be equal to work. So in other words, when a mass experiences some acceleration and that acceleration causes a displacement of the object, then we would say work is done. And we know applying a force requires energy. So therefore the unit of work is the joule, which you probably remember from chemistry, where you talked about energy. So the unit of work in science is the joule. In our terms, we're going to describe it as newtons times meters. So we'd get that literally from this equation. The unit for force is newtons, and the unit for displacement is meters. So it literally works out to be newtons times meters. Just to give you an idea, 1 joule of energy is the amount of energy you would need to raise an apple 1 meter off the floor. So a joule is not a huge amount of energy. It doesn't take much to lift an apple 1 meter off the floor. So that just hopefully gives you an idea of what a joule is. Let's look at some different situations here. So is work done in each of these situations? So holding 2 textbooks at your side. Well, there is a force. The force is applied up, but there's no displacement. So force has some value, but displacement is 0. If our equation for work is work equals force times displacement, if displacement is 0, then work is 0. So this would be no. There is no work done in this situation. If you hold 2 textbooks at your side and walk 2 meters, is work done? The answer to this is also no. And it's weird for some students, but this is actually no work is done. Our definition is the product of a constant force which causes a displacement. So look at this picture. What direction is the force? The force is you holding this textbook up, and the displacement is to the right. So is this force, the force of lifting, causing this displacement? No. So you could walk 100 miles carrying 100 pounds, and scientifically you would have done no work because your force, the force of lifting, is not causing the displacement. Other forces are, and their work would be done, but in terms of your arm would have done no work scientifically. If we keep going down, you pick up 2 textbooks from the floor and lift them over your head. So now the force is you applied. So there's the force, and the displacement is some 2 meters over your head. So in this case, yes, work is done because the force and the displacement, the force, the lifting force, causes the displacement. Pull 2 textbooks in the basket with an angle at 30 degrees, a distance of 2 meters while something. So it doesn't matter. Here in our picture, this applied force is causing the displacement. So in this case, yes, work is done here. We're going to look a little more closely at the definition of work in a moment, and what we're going to see is not all of this 50 newtons is actually doing the work. So we'll talk about that, but in short, yes, some work is done here. If you push 2 textbooks across your lab table, again, yes, this would be work. The force is in this direction, the displacement is in this direction, so yes, this would be work. And then a lift slowly lowers an object to the ground. So this one's interesting. Is work done? The answer is yes. Yes, work is done. And the reason students often say no to this one is because the force from the lift is up. If the lift wasn't here, then the only force would be the force of gravity, and this would fall straight down. So clearly the lift is applying some force, and this force, while it is up, is related to the displacement of this object. It is related to it. It is what's slowing it down. So in this case, yes, work is done. And we're going to talk about the sign that you get for work and what that actually means. But in short, since this force is related to the displacement of this object, it's applying a force that slows it down from going into free fall, then yes, work is done in this scenario. So let's look a little more closely at our definition of work. So work is being done. This is just like the other one. There's a force being applied. That force, this pulling force, is causing the displacement to the right. What we know from previous, though, is that this force can be broken into components, right? So there's a horizontal force and a vertical force. So this would be force vertical, this would be force horizontal. If we stop and think about it, only the horizontal force is causing this object to accelerate. The force in the vertical direction is not related to the horizontal force. We learned that in the last unit when we looked at vectors and forces. So this force, this component of the force, is doing no work. It's not causing the displacement. So only the parallel component to the displacement is doing any work. And so really when we talk about work, we want to think of it as work is force times displacement, but we can think of it more specifically than that. Since only force components parallel to the displacement are considered when calculating net work. Just like in this picture, the vertical force is doing no work. It's not related to this displacement at all, so we don't care about it. So we can more accurately describe work by saying the force times the displacement times cosine of the angle. To let you know where this is coming from, if we did this problem, the work of it would be equal to the displacement, how much displacement is there, but since it's only the horizontal force that's acting, we could write Fx. We could write it, we would say Fx, the force's horizontal component, but another way for me to describe Fx would be force applied times the cosine of whatever angle that is. This, we know from our last unit, is how we would determine, we would take this, the hypotenuse of the triangle, use cosine of the angle, and get this component. And so really what we do when we write this out, the long form is saying whatever the force is, take the total, or the hypotenuse of it, times it by the cosine of the angle, and then multiply it by the distance. And we will have the total work done. And so that's kind of a shorter way to figure it out instead of first solving for the component and then timesing it by displacement. You can do that. This equation puts it all into one step for you. When we experience situations where there is more than one force acting on an object, all forces parallel to the object's displacement must be considered. In other words, we have to consider the net force that is related to it, as always. So in this case, there are two forces acting parallel to the displacement. So the displacement here is 0.8 meters to the right. So we're moving along this conveyor belt. There is the force of gravity, but we don't care. It doesn't relate to its displacement. There is the normal force. That also doesn't relate to its displacement. So the only two forces that are related to its displacement are F applied and F, force of friction. So when we used our work equation, to get the net work, we need the net force times the displacement times, and if we're using our long equation, it's times the cosine of the angle. Well, what's the angle here? The angle is 0. If you do the cosine of the angle, you're going to get 1. So ultimately, this whole root doesn't actually matter. So we would need force net. Force net here is going to be, force net would be equal to force applied plus the force of friction. So I'd end up with 120 plus -5. So the force net would be 115. So I would do 115 times 0.8 meters, and that would give me the total work done. Last thing we want to look at is the sign of work. The sign of work is really, really important, because in our last example here, we would have taken 115, so it's 120 plus -5, right? These are vectors, they matter, so we have to consider sign. So we would end up with a net force of 115 newtons times 0.8 meters. This is overall going to give us a positive number. However, if we had ended up with a negative number, then that would mean our work would be negative. And so what does that actually mean? So sign of work clearly matters. Positive work is when force and displacement are in the same direction. And so we would be adding energy to the object. Just like the box in the last example would be speeding up or accelerating, that's because energy is being added to the box. So the object is speeding up. So in this case, positive work is done because the force and the displacement are in the same direction. So in this picture, the student is lifting the box. So we would say the force applied by this student lifting it is in the same direction as this object's displacement, and so therefore the work done, it would be a positive force and a positive displacement, so we would say work is positive. The box would be speeding up, the boy would be adding energy to this object, and therefore it would be positive work. But that's not always true. So you can actually have negative work. Negative work is when force and displacement are in opposite directions. So that would result in energy being taken away from the object, or the object slowing down. Often this is due to friction. So here we would have the force, we could call this force net. This could maybe be the force of friction of a sliding object. Its displacement is to the right, so we would end up with a negative force value but a positive displacement, which would mean when we solve for work, force times displacement, we would end up with a negative number. And that we know that this box would be slowing down as it moves to the right if friction is the only force acting on it. And so we can look at a couple different examples here. In this case, if we could look at this problem in two different ways. And so this is why it's important you read the questions carefully, because in this problem there are two forces. So we've got the force applied and we've got the force of friction. So in this case, then the lawnmower's displacement is to the left. So in this case, the force applied would be a negative number and the displacement would be a negative number. So work would be force, negative something, times displacement, negative something. If we look at the work done by the applied force, the work done by the person, work would be positive. If we look at the work done by friction, so the force would be to the right, that's a positive number. The displacement is to the left, that's negative. So if we looked at the work done by friction, then work would be a negative number, right? And if we know, or if we think about it, we know friction slows an object down. So therefore, the work done by friction would be a negative number. because its friction will be opposite the direction of the object's displacement. An interesting way to think about this is doing a push-up actually is negative work. So where's the force here? Well, the force is coming from your arms. If you did not apply a force when doing a push-up, then you would just be falling to the ground. And so clearly your muscles must apply a force, and they apply that force up to slow your descent as you go down. And yet your displacement is this direction. So therefore, we end up with a situation where the force applied is up, or positive, and the displacement is negative or down. So if we multiplied a positive force by a negative displacement, we would end up with work being a negative value. And so, as weird as it is to think from a science standpoint, a push-up is negative work. So I guess that means we should all be able to do infinity push-ups, because technically we're doing negative work. Unfortunately, it doesn't work like that in real life, and we'll get into energy more in this unit. So I hope this helps as you kind of introduce yourself to what is work and energy. There's also the text available and some other videos if this one didn't help you. And as always, if you have questions, please email me and let me know.